All right, so today we have my wife, Cami, and Zach Zabala, who is Good Times for All. And they have been working very hard on this presentation for, gosh, at least a couple of months here. This is the very first time that they've ever done a presentation at FEIC. Actually, it's the first time they've ever done a presentation, so. So, yeah. So anyway, they've done a great job on it. It's all about how the world works, and through some of the observational experiments they have done with magnets and lights and everything like that. I think you guys are going to enjoy it. So please welcome Zach Zabala and Cami Knodel.
Hi, everybody. Can you hear me okay? All right. Thank you all. We're a little bit nervous. We're not professional presenters at all, but we're really, really excited to be here and really excited that you're all here. On the audio, while they're working on the audio, and tell me when I'm doing things wrong, I was going to take the end part of the presentation and some of the talking part and go through it while we're waiting to get the actual presentation, so you're not sitting here. So while we're waiting for this, we'll have some fun. And with how the world works, we're covering two things. When we get into the thing, a lot of it will be going into things that we know work. Towards the end of it, we are going into possibilities. And that's where we're starting with now because of the fact that they're getting our presentation up. I'm going to welcome Zach, and then I'm going to go into a possibility of holographic skies. So, Zach?
Hi, everybody. Hope you're all enjoying yourselves here. The speakers so far have been wonderful. The atmosphere is just, it's electric. I love being here. Thank you all for joining us. The presentation, we're going to cover a little bit of perspective. We're going to cover the electricity and the electric field, how it manipulates the world around us. We're going to get into gyroscopes and magnets, how they interact with each other. And then, like Cami said, we're going to be looking at how the planets move in the sky, how they actually move. We'll get into that later, but Cami, this is pretty much Cami's brainchild. I am not a presenter. We're both lab nerds. We're the guys sitting in the lab fiddling around all the time. But when she asked me to do it, I couldn't turn her down because I want her brain to be shared with all of you. This is her baby right here. And she's amazing, and I will give you back to her so she can start talking about the miroscope.
We're going to do this presentation entirely backwards. And so we're starting from the reverse right now on a possibility. And one of the possibilities, when getting in this, I'm a curious being. I'm the nerdy side of Bob. Bob is very technical, but I am the nerdy side, and I always, always want to know, how does it work? How could it work? Some of the things we do know how they work, and some of the things we're doing are possibilities. So when looking at the sky, we look at problems that you encounter with the sky and where you see things from angular perspective, and where we can't make the math work out exactly, or why do you see only the bottom half of the moon? So I started looking at alternative cosmology, and alternative cosmology, or ancient, not alternative, but all of the cosmologies, I found showed that when they did things, they showed that we have different layers going up. You have Sheol or hell or the underworld. It depends on what cosmology you look at. You have Earth or Terra and the dome, the magnetic dome. And most people are calling that the firmament. And I disagree because, and this is a possibility, I have looked at all different cosmologies, and they list Earth and the dome, but then they talk about the firmament. And they talk about it, like in Christian religions, they call it a vault of looking glass. They talk about when you cross the river to hear the golden bells, if you're familiar with it. They talk about it in Egyptians, you talk about them crossing the river. No matter what, there is always another layer above us, and it's always described as a river, looking glass, shiny. So I got to thinking, what would happen if you actually took a vault of looking glass? And it turns out that there is a toy that you can buy, a child's toy. And it's called a miroscope. Oops, I'm very loud. And it is just a vault of mirrors. And that's all it is. But what it does, oops, I'm all over the place. What it is it's a natural hologram emitter. So what happens is if you actually if you sit there and play with what they describe as a vault of looking glass, you all of a sudden have a natural hologram emitter that, let's see. Oops. Forward. Oops, and this is going for it. This is showing that the hologram is going to, produce whatever you put in the dish. And you guys can come up and look at it. It makes an actual, you can't see it from this level, but you'll do it here. It will actually produce the hologram of what you put in the dish. But unlike holograms that you're used to thinking about, you guys are all looking at digital holograms. This hologram is amazing. This hologram not only propagates into domes through Polaroid filters, through every type of filter, but also if you put a piece of ice into the miroscope, you have an actual experiment that we could be running, but you guys are listening while they get our audio up on the experiment. If you put a piece of ice into the miroscope, into the little children's toy or a vault of looking glass, the hologram will register a colder temperature. The actual hologram will reflect. So it's not only reflecting, if you put something hot in there, your hologram will be hot. It's not the rays right above it. We take the thermometers, we test all around it. It's the actual hologram that's doing it. It's going to get better that if you take a UV light and something that fluoresces and you put it in the holoscope, you can create light not only by hitting it inside the dish, but if you actually take, and I'll have a video of it hitting the hologram there, the hologram will actually, UV will fluoresce the hologram itself. Not the object itself, you can do both, so you can create light that way. I think I'm going to play a little visual. There's a black one. And we are getting ready. This shows the hologram propagating into like little things. It goes through filters, it pops up everything. Everything you're looking at is a mirage on the screen. Forward. That's showing it upside down. Again, just forward. Polaroid filters, forward. This was towards the end. This is in water. It's wonderful when you actually put water in there because I believe it is fluid. What it does do is you'll notice on some of the pictures in close, because it's sitting on the mirror, you get a mirrored reflection. As soon as you raise it up in fluid, that is a hologram you're looking at with water. So what you're seeing, and you guys are welcome to come up here and play, but it's just, again, a possibility of doing that. One more, can you click me? Oop. We're showing different configurations because I believe the firmament is above us, miroscoping down in, and I'm looking for a video. This is just making the projects, because again, we are not in order right now. These are some pictures of it lit up, and I think we're going to hit a video in just a minute. Go ahead. That one you should be able to play. It should be a play video. Oh, it is. I know it is. Oh, you guys can't hear me in back. I'll speak better on there. Okay. Yeah, I'm sure. And there's other ones on it that are played. That one should be played too. In the presentation on there, can we bring it up on the computer without there, just on the regular, not the presenting side, the other side, so I can bring it up? Pardon? Try, you ready? Okay, can you help us up here on how to? Okay. Okay, this should be playing. Does anybody know how to run PowerPoint that can get us to run this? My husband got called out. Karen B. Woohoo! I knew Karen would be on the stage with this. These are videos. That one might not be the black ones. The ones with the black spots were videos. Go back to a different one. It had asterisks. That's a video. That is a video. It was on the, oh, okay, I'm talking into this. I'm gonna let you talk a minute.
Sorry about this, folks.
We practiced it, we had it all perfectly, and it ran, and then the configuration came out. It's a first prisoner's nightmare.
Can we see if the video is...
It is a video, it's a great video.
Okay, folks. Once we start the videos, No, the fishbowl wasn't the hologram, just a little object inside.
I layer them. We would think that your cosmology would have the firmament above us, and it would be literally. Oops, I would do this. So it would be above us, and the hologram would be what we see in the sky. So it would be, the dome would be the dome. So I believe that what we're seeing is propagating from here. And this is not even a belief. This is just a possibility that we're looking at things and saying, how could that possibly work? And wow, this is really, really fascinating. Especially the fact that it does transfer light, and especially the fact for the people that, with the miroscope, if we can get the videos running, because they're cool. Oh, can we make it on? Oh, yeah. Go ahead and watch the big screen and see what's playing. Okay, here it comes. You're gonna watch a light coming. What you're seeing is I'm just using a UV light in a dark room, and it stopped. It should keep going. That light was moving. Aha, perfect. Okay, so here's like a miroscope going, and it looks like it's gonna play. Okay, and I'm moving a little hand light there. It is hard to see. And let's see if we can get it, because you can actually, by moving it, create the phases of the moon, which we'll talk about in this, which would create themselves naturally. Can it still, we haven't got it to actually play, just the first few seconds. You did have it playing. But what you'll see with I wish, because I cannot do a hologram for all of you guys and get the angle right for you as above. I don't have a big enough miroscope and even traveling with, so we're trying to get the video up. But what's interesting of it, it would be above there, it would be holographing into it if it's working like this. And what I did find interesting about this is when I took hold them. When I took two of these, we might have the video going. Okay, light is moving, watch. There's another one that's showing it better, and you'll see it's actually lighting up. We're hitting the hologram itself, and you guys can do this. The hologram itself will react to UV light, will react to temperature, will react to everything. And you'll see like the phases of the moon coming in on this. This is playing. The other thing about the miroscope is if you use a double miroscope with two holes and put something in the middle, it will make the holograph above and below. And I think we might come back to the miroscope, because I think our presentation is ready to go. No, but it doesn't matter. We're going to come back to the miroscope. We did it out of order and take it back to the front. And I'm going to let you guys, anybody at the end, come in and can show you. And again, this is just a possibility that if the firmament is a ball tip looking glass, you have a natural hologram emitter. I don't know if that's what it is, but that is how it would work. And if we take it all the way up to the front, the very top, very top, Karen. Number 1, I think we can just, the very first one. I think I want to start on 1. Just start on 1 and let it run. And I apologize again. We do have glitches, and they did pull my husband in another one that was going to be running it for, so we're a little bit confused. Okay. Is that better? Better, everyone? Yes. Is that better? Am I not talking loud enough? Okay, it sounds very, very loud to me. It's echoing, so good. Okay.
How the World Works by Cami Knodel and Zabala.
In this presentation, we are going to show you the way in which we have measured the world to be, and then some possibilities of how the unknown creates and shapes this beautiful world we call home. We will be delving into how we visualize this place and the limits in which we may do so. We will look at electricity and magnetism, both the laws which govern them, and then occulted knowledge that is hidden in plain sight. We will be using many tests and observations we have made and documented ourselves, along with others we have gathered from academia and content providers who have shared their research on social media platforms. In the end, we are hoping to share something with you that you did not already know, or at least open your mind to some new possibilities. As my favorite quote from Plato goes, those able to see beyond the shadow and lies of their culture will never be understood, let alone believed by the masses.
Okay, folks. Hello? Okay. In the first presentation, or the first video we're going to be watching, we are going to be taking a look at perspective. Now, this is just a fundamental limitation of how lenses work, and it has nothing to do with atmosphere or any other dust particulates, things like that. This is a limit of a lens with a certain size aperture, and this can't be refuted. This is a fundamental limitation of the physics of how perspective works and how any lens with a circular aperture is going to have a diffraction pattern across the center. I just wanted to make it clear that I say it in the video, but I wanted you to know that refraction, any kind of atmospherics, this will not be covering that at all. This will show you how on a flat plane, even with no atmosphere, things would sink from the bottom up, would disappear from the bottom up and look like they're sinking into the ground. Here we go. A fundamental limitation of perspective. First off, we will be taking a look at perspective and the limitations of not only our eyes, but any lens with a circular aperture. This covers most cameras and telescopes, along with the vision of every human being on Earth. All of these lenses share what is called an angular resolution limit, which simply means that once two light sources get close enough together, they will merge into one, blurring the image. This is all determined by the size of the aperture, or hole, which is allowing the light to shine through, like the pupil of your eye, for example. Here are some students from Brigham Young University showing how the aperture can create this effect at the same distance just by changing its size. Next, we will take a look at some observations I made along a long warehouse floor up to 460 feet. As you can see, as I back the camera away from the bucket lids, the bottom creates a mirroring effect. The mirror grows larger until the actual lid and its mirror image start to appear to merge together. Another, taken with a flashlight, also shows a mirroring effect followed by them merging into one and then completely disappearing into thin air. David Weiss has captured this with the sun while tracking it with a drone multiple times. This diffraction pattern we see here can be calculated using a formula known as Rayleigh's criterion, and with this we find the average human eye to be around 0.02 degrees. It is radians equals 1.22 times lambda, or the wavelength of light, over d, the diameter of the aperture. The part of the equation which we want to concentrate on is the d. You can see that with it on the bottom, the larger it is, the smaller the final result will be. With this formula I wrote, you can easily figure out how much will always be hidden along your horizon when looking out over a long distance. A minute, if you will. When a boat gets to only 3 miles away, right around when we are told it should be going over a curve, there is over 5.5 feet that the human eye cannot resolve. You can watch it go out of sight with your eye's vision, then use a lens with a much larger aperture and bring the whole boat back into view. This drawing will show just what is happening and why we can somehow magically see an object which was believed to have gone over a solid barrier horizon without raising our elevation. This is because the larger aperture, the smaller the angle that can be resolved, as the equation showed us. With the average human eye losing the whole boat except for the sail at this point, you can now see why the camera with a much larger aperture can resolve the whole image once again. This is a fundamental limitation of physics pertaining to any lens with a circular aperture. However, this calculation does not take into account any atmospheric distortions and can only become worse in reality, as it is regarding to a perfect nitrogen-oxygen-based atmosphere with no moisture or dust particulates floating about. In short, the appearance of boats going over a curve, the bottom of buildings being cut off, and the luminaries in the sky appearing to set can all be explained over a flat surface with the fundamental limitations of our eyes alone.
All right.
Thank you. So pretty much we just showed that even with no atmospheric distortions, the way our eyes work and the way lenses work, things will disappear from the bottom up. Things will disappear. It's just, and this is one of the things that they've hid from us. I think they've reversed engineered our perspective and made the Earth curve according to that. I think so many things have been reverse engineered, and perspective was one of the big ones that they had to come up with a reason why things were the way they were. And that'll be it for the perspective part of it. I'm going to hand it over to Cami, and she's going to explain how a gyroscope and a magnet work together.
Actually, we're going to play the video, and we're going to take you right to the video. The gyroscope and the magnet. In this next segment, we will be taking a look at the forces created by gyroscopes and magnets, how they are applied to our devices, and finally, how they interact with each other. The gyroscope, invented in 1743 by John Searson, was first called the whirling speculum and was used to identify the horizon in bad weather. Today they are used by many without us even knowing it. Gyroscopes are used from navigation tools for aircrafts and ships, sensors in your cell phones and watches, all the way down to a child's toy you yourself may have had at one time. The special property they possess is that once spinning fast enough, the gyroscope will obtain its rigidity in space. This simply means that no matter which way you tilt or rotate its mount, the gyroscope will be unaffected and hold its position in space. It has been claimed that the mechanical gyroscope can detect the motion of the Earth using this phenomena, but many failures to do so have been documented by academia and truth seekers alike. In a version of Popular Astronomy from 1922, we found this by M.C. Mott-Smith. One must often wonder whether the authors of these texts really ever performed the experiments they describe. Where the divergency between theory and fact is so great, as in the case of the gyroscope, it certainly should not be dismissed with a vague remark or two about friction. While the theorist may care little about it, the practical man naturally wants to know why the actual gyroscope behaves as it does. The more sensitive fiber optic and ring laser gyros do detect a motion, but we are not certain what causes this phenomenon. The magnet. Like electricity, magnetism holds many secrets we have not yet uncovered. What we do know is that every magnet produces a magnetic field, which can affect the world around it in many ways. Magnets, which interact with many metals, are used much more than gyroscopes and are no stranger to most of us. From children's toys and holding up papers on the fridge to industrial purposes used to lift enormous amounts of weight. Some have even replaced the pencil and brush with little magnets to express their artistic talents. The uses for magnets are endless, and we still haven't fully unlocked all of its secrets. We will now look at an observation we made while applying a magnetic field to a super precision gyroscope at rest, compared to one in motion at different speeds. When we hold a magnet near the motionless gyroscope, you can see there is a slight attraction only when one of the poles of a strong magnet is facing it. This is unusual, as brass and aluminum aren't magnetic in nature. The strangest thing is that once spinning at high speeds, the magnet will repulse or push the gyroscope away. This can be attributed to Lenz's law and shown in this quick demonstration. The magnet's descent is slowed as it passes through the brass pipe due to a current being created in the brass. This current then produces its own magnetic field, which interacts with the magnets. The question is, could these fiber optic and ring laser gyros be picking up the movement of the ever-changing magnetic field? It's available. It's all out there for you guys to try things and experiment yourself and to try. The hands that you see on this are us. It's not there, but gyroscopes are, I don't know if you guys heard that again, it's affected by a magnet, but it's not magnetic. So there are really, really amazing things to think about with this. And we're going to take you next to electricity and the electric field. We have to keep our intros quick because we lost time on it.
Electricity and the electric field. We could be here for days discussing electricity and what we as human beings have discovered so far on the subject. Instead, I will let Walter Lewin, former MIT physics professor, put in few words the importance of understanding electricity and how crucial it is to continue to investigate the subject further.
Electricity and magnetism is all around us. We have electric lights, electric clocks, we have microphones, calculators, televisions, VCRs, radio, computers. Light itself is an electromagnetic phenomenon, as radio waves are. The colors of the rainbow in the blue sky are there because of electricity, and I will teach you about that in this course. Cars, planes, trains can only run because of electricity. Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could not see without electricity. Your heart would not beat without electricity. And you could not even think without electricity, though I realize that even with electricity, some of you may have a problem with that.
As you heard from Professor Lewin, electricity governs how we perceive this world around us, and furthermore, the world itself. This is the electric field of the Earth and starts at the ground with a negative charge, obtaining more of a positive charge from above, increasing with elevation. We know from measurements that the electric potential in the air increases with altitude. Starting at 100 volts per meter just above the surface, increasing that same amount with every meter gained in elevation. So just above 2 meters, or 6.5 feet, there will be 300 volts of electricity in every cubic meter of air. You may think this is a large amount of volts to be floating just above our heads, but it takes 3 million volts per meter to have an electrical discharge occur. We will now take a look at some observations we made to see what we could achieve by creating and manipulating our own electric field and placing different substances between it. In our first test, we simply charge up 2 metal plates, making one positive and the other negative using a Van de Graaff generator. You can see in the demonstration that by simply switching the positive and negative charges of that which we find here on Earth, we can get very light objects to rise up from the positive plate below and stick to the negative plate above. We do not believe that this itself causes gravity, but may be what gives it its direction as far as up and down. In this next demonstration, we are going to take a look at what the electric field can do to the surface of water. We have a spherical object painted with metallic paint and held up by a wooden insulator with the Van de Graaff generator beneath. When a charge is applied, the water takes the shape of the electric field at its surface. This reminds me of this map created long ago using the stars as its reference. Now we will look at the nature of the electric field and why it must bend and curve between two objects that aren't perfectly parallel. When it comes in contact with the surface of any object, it will always be perpendicular to its surface. This simply means it will be touching the surface at a 90-degree angle, as you see here in this picture. All in all, electricity governs not only our senses, but the physical world around us in more ways than we will most likely ever know. The movement of the planetas. Humans have been studying and documenting the luminaries and their paths since before writing began. Claudius Ptolemy and ancient Greek had over 900 years of observations to reference before Christ had walked the earth. He believed the earth to be at the center of the universe, with the sun, moon, planets, and stars all revolving around it. This is known as the Ptolemaic model and was considered the model of the heavens for over 1,300 years. Not until astronomer Tycho Brahe, born in the 1500s, came up with a model using newer, more accurate measuring devices. In his model, the Earth was still at the center, but now the planetas moved around the Sun as it circled the Earth. Soon after, the heliocentric model was fabricated and the geocentric model was set aside by most astronomers. Today, we look at the luminaries with opened eyes, now above a flat, motionless plane, and new questions arise. What causes these movements? Is there anything in nature we can observe that can recreate the paths followed by the planetas? Looking into magnetic field lines has brought forth some amazing similarities. Now, we have not measured and documented these motions for ourselves and have found many that contradict each other. This is the path of the different wandering stars above our flat plane in the Ptolemaic model. They are actually all stacked upon each other, never traversing outside the tropics of Cancer and Capricorn, but are spread out in this animation to show their paths without overlapping. When looking through a ferrocell, using different numbers of light sources, we can recreate these motions path with a single magnet. No matter the true patterns, they all have similarities in all the models we find. The real question is, with Newtonian and Einsteinian gravity never proven, is a magnetic property the answer to what directs the paths of the wandering stars?
Joaquin and Boaz. The two pillars have been a symbol of an entryway into the unknown, both physically and spiritually, for as long as our ancient history has been recorded. From Samson collapsing the two pillars and bringing the ceiling down upon his captors, to the mighty Hercules, marking the end of the known world by splitting a mountain to create an opening to the perilous Atlantic Ocean. Many of the old cathedrals have two large pillars aside an arched entryway leading into the church. Even modern buildings have this incorporated into their architecture, almost hidden in plain sight for those who have eyes to see. The first mention of the pillars, Joaquin and Boaz, comes from the building of Solomon's temple and goes into great detail, the materials used and their dimensions. Many secret societies mark entrances into their sacred places with two pillars and has even a deeper meaning when looked at spiritually. From the ancient tarot card murals to modern art of secret society members, the two pillars have represented the path into the unknown and the paths one must follow to create the tree of life. Ancient alchemical text, the Kabbalah, Egyptian hieroglyphs, all the way back to the oldest Sumerian tablets mention the tree of life. the Mayans, Incas, Aztecs, Norse, Kemetic, and Celtic, just to name a few, all have their own tree of life mythology. The tree is meant to represent the Sephiroth, which are the realms that create this place we live. As you can see, they all have a very similar, if not identical, layout for the path to enlightenment. The two pillars create an opening, or a third pillar to ascend upon after death. You can see from these Masonic drawings that the third pillar in the center create a stairway, or a ladder to ascend upon. Now we will try to apply this to the earth we live upon, and how its magnetic field could be created using two pillars, which in turn creates a third pillar, or maybe our magnetic North Pole. When two opposing magnets are placed next to each other, a third magnetic pole will be created in the center. The magnetic field of Earth that we are given is in a four-leaf clover pattern that centers at the North Pole. The ocean tides also seem to follow this pattern. When you place the two pillars correctly, one can create the same magnetic pattern we are given. So the question is, do we need a magnetic mountain at the North Pole, or is the ever-changing magnetic field we measure created by other means, which are hidden in plain sight? Joaquin
Hello, hello.
Oops, perfect. Can you bring up the magnetic pattern on the... Yeah, perfect. Do we have a pointer? When you were looking at the Ferricel work on it and the moon phases and that, the pattern that was created, we did that by taking... Oops. I think I might be doing... Is that me doing this? Yes. Okay. Top button. Bring me back. All right. This is what happens when you have newbies. That Ferricel pattern on the pillars is we took two pillars or two magnets, dipoles. You have a dipole here on your magnetic map. You have a dipole that's coming to get her off. But you'll notice that this is Earth's declination. This is not from me. This is from magnetic declination maps. USAA maps in this. All we did is turn it into an AE projection. But you'll notice that they say our Earth is a dipole. But if you look at this pattern, this is not the pattern of a dipole or a north and a south pole on an axis. You'll notice that the center of it has a quadrupole. 1, 2, 3, 4 poles. North, south, two dipoles on the side. We actually created the quadrupole by taking two pillars. It will create a magnetic field that matches what's on Earth by actually taking two pillars. It creates the third magnetic field, and so that's some of the things we're playing with in laboratory with the Ferricel. Reasons we don't sleep at night playing with the magnets and things. So I hope you all think it's as fascinating as I do. I'm in awe of it. The things that you can do in that. Looking at it, does anybody, because of the way it went with the audio and that, we went completely out of sequence. Do we have any more things to do, or are we okay? Do we have any other videos or no? I think we made it through. So I think, and I know that we're late right now, but we pushed it through in weird order. We meant to do it, talk in between, and then go over like the mirror scope or stuff with time afterwards. We are now like finished with time, but we'd like to open it up for any questions before you leave or anything you'd like us to cover. Go.
Did the magnet react with the brass both when it was spinning and not spinning, or only when it was spinning?
Yes, when it's spinning at a high RPMs, the magnet actually would push the gyroscope away. It wouldn't attract to it. Now, when it wasn't spinning, we would get a little bit of attraction only when one of the poles of the magnet was very close to it. Yeah, brass and, I mean, I could touch my magnet on it and pull it off real easy. There's no super magnetic attraction. But on one of the poles, you can get it to move just a little bit. And then once you speed it up and get it, I think it was above 6,000 RPM, 7,000 RPMs, you take that magnet and you put it next to it and it'll actually push the gyroscope away. Yeah. Yeah. Yes, sir. On the flat Earth model? Yeah, that's the thing. The second part was all about things that we're not sure of because, for starters, we haven't measured the movement of the planets yet. That takes years and years and years and years to get, I think it's 27 or 28 years for Saturn to go around one time in its orbital path. So we haven't had the time or the resources to actually measure it ourselves, so I don't even know if they do what they're telling us. Yeah, it's definitely something we're going to be researching a lot and looking into a lot more in the future, for sure.
It's exactly up our alley. It's exactly what we want to be doing.
Yes, sir.
Have you or anybody else in the room thought of how to tell if there is a South Pole? North Pole's easy. Has anybody thought about that at all?
He's asking if anybody has wondered about the South Pole.
So, I'm looking at this map. I know you took a look.
I will. Do you want me to fill this one a little bit?
Yeah,
and give
go
it
ahead.
to you? I need the microphone. Okay, he's asking if anybody can test for a South Pole in that because it is somewhat, and this is the way I'm going to do it is I know everybody is saying the South Pole is going all around the bottom, and I'm going to say that, again, these are in the possibilities, things that we don't know, but looking at the magnetic map that we have, I actually lean heavily towards I would call it a 3-pole series that we would have, oops. I don't know why I can't work things, oops, right there. Okay, we would have one dipole here. You have where the red and blue come off and are gonna make another point right about out here if you extrapolate and finish the patterns. And here is what we're calling our North Pole, which actually registers as a South Pole. I don't know if you guys know that, but that's a deception. If you do magnetics, what we call the North Pole is the South Pole in the magnet. That's just something flipped on it. Something reversed. So this would be really the magnetic South Pole, even though I have a quadrupole running. It's the way that the compass is reading them. I think this is all part of the deception, and especially I'm measuring the south. I think we're going to have places we can mark them here and here. I believe that we do have magnetics here, and this is just my beliefs, my personal beliefs, from what I'm gathering from the magnetics and what I'm getting at the patterns and working with and recreating things. So I don't know if that answers your question, but your question is some people say it's going all the way around. I'm thinking that we have 2 specific points where magnetically are going to show a lot stronger. And the 2 magnetics are where people are going to think the South Pole would be, if you look at it, the map, under Antarctica, and then taking between South America and this. In other words, it's going to work out that if you look at the declination and where you would look to where the other pole would be, so they're going to read it that way magnetically. Most people are going to say on it is going all the way around. Our magnetics are not that of a ring magnet. Our magnetics, we simplify it. Our magnetics, if anybody knows magnets at all, they have amazing qualities. The quadrupole pattern on here can be created by 2 magnets side by side, 4 magnets top down, or if you make, this is the exact same pattern produced with this is an anti-Helmholtz, the way it's showed, or a Helmholtz coil. So if anybody is familiar with Helmholtz coils and the properties they have, our field is much more equivalent to that, which happens to be, has qualities like field stabilizer, equalizer. They have properties, magnetic trapping, things that we're looking at and for, but it's not just a simple ring magnet or that pattern, really, when you get down to it. And I know that we are past time here, but we're going up against lunch, so everybody, you're welcome to stay and ask more questions or do this, because I believe that, I think we were out of time like 5 minutes ago. But thank you, everybody, for coming. And if anybody has more questions than that, we're not going anywhere. It's lunch. Go ahead. Yes. The hologram, we have that on tape. If anybody wanted to see it, if we wanted to hit the thing on it, we can even show you. If anybody wanted to see on the Geeks, we have. What would cause that? Yes, I have a brief idea. In other words, when we think of holograms, we think of digital holograms produced that way. What this is doing is this is actually mirroring all of the waves, not just the visual. It's because it's working much more gracefully than a hologram, a digital hologram program thing that only picks up visible. I believe what's going on is this is reflecting all of the rays, the whole spectrum, everything.